This is POE section 2.1.3 free body diagrams. A free body diagram is a visual representation. It's a picture that you draw of force and object interactions, or how forces interact on different objects. So we're looking at individual objects or the members of an object and how they're isolated from their environment or system, showing all the external forces acting upon them. Here we have a bridge. Here we have a pulley with the different, these here on the sides are going to be our different, the strings that the pulley is hanging from, and we'll go into detail for quite a few others. So a force is a straight line push or a pull, and it's acting upon an object. We're going to look at vector quantities. They have both a direction and a magnitude. Direction is set up by an arrowhead. So these, the middle one there has a direction up to the right. This one has a direction of up and to the right. Magnitude is going to be illustrated by length of the line segment. For this class, you're always going to have a number given to you. It's not just going to be the length of the line segment. It's not feasible for us to keep track of that in a class of this size. So let's talk about the moment again. The moment is a twisting effort. It's another way of thinking of torque. And it's about a point or an axis when a force is applied at a distance, especially. We look at moments, and they're drawn this way. As an arc with an arrowhead, we've got a clockwise and a counterclockwise. Clockwise goes around to the right. Counterclockwise goes around to the left. CCW is counterclockwise. So let's kind of review moment. We haven't really talked too much about moment since we were talking about simple machines at the beginning of the year. So moment is a force times a distance. We're looking at perpendicular to the line of the action of the force. So this distance that we're talking about, here in the center of this nut is our point of rotation. I apply a force where this says line of action, so I apply a force at the end of the wrench. The distance is from the point of rotation over to my line of action, or where I'm applying the force. So it is perpendicular to the force. The distance has to be perpendicular to the force, otherwise you're not really looking at a moment. So let's look at the various steps for drawing a free body diagram. In this case, we're going to draw a free body diagram of the DE book there at the top of the stack of Project Lead the Way books. First thing you want to do is sketch the object. In this case, we're looking at the top book, so that's all we're going to draw. So here I have my top book. The next one, they're asking us to sketch the applied and norm forces. A norm force is a reactionary force. If I have an item sitting on top of something, the norm force is the force that keeps the item from going through it. For instance, in this case, the applied force is the weight of the top book. The norm force is a reaction force pushing up on the book, keeping it from falling. So I have a normal force coming up out of the book and an applied force going through the book into the books below it. Step 3 says to label the objects and the forces. In this case, the DE book weighed 5 pounds, so its weight is 5 pounds. This W stands for weight. So its weight is 5 pounds. The normal force is 5 pounds. The forces going up and down need to be equal. If they are not equal, either the book is floating on its own or it's falling through the other books. We also then label the DE book. Looking at the dimensions, in the case of the book, it's not relevant that I draw it. And all this complicated set of triangles here, this is what we'll be working towards, but you want to make sure that you put in the proper, all the dimensioning, including the length, height, angles, and any other information that would be useful. In this case, we've got our distances drawn out this way. Our forces are all marked and identified, so you want to do anything you can possibly do to make it as easy to draw the drawing as possible. Here they ask you to create a free body diagram of the sled that's below. Make it simple. The sled becomes a box. I have the weight. I have the force of friction, which we actually won't talk about much in this class. They try to keep it simple. We have the normal force to keep the sled from falling through the ground. And then I have the applied force of pulling on the string or on the rope to pull the sled. and that's at a certain degree from the ground. That allows us to break that force of application, this applied force, into different component forces, both the X and the Y versions. Create a free body diagram for the refrigerator. Just the refrigerator. So I turn a refrigerator into a block. It has a weight that goes straight down. It has a normal force that you see here on the coming out of the ramp into the refrigerator. The normal force is what keeps it from going to the ground, and that is at an angle. It is not the ground below the ramp that is putting the normal force. It is the ramp that's putting the normal force onto it. And the applied force is the force that's being pushed in from the mover moving the refrigerator up the ramp. And here we have it moving out of our block. Force of friction, which we won't talk about, and then we need to look at angles. To create a free body diagram of the pulley, so let's look at the first portion. This has got two different pulleys in it, so we'll look at both individually. I have the weight, I have a tension force. When we're talking about pulleys, we're going to talk about tension forces. When we're talking about cables, we will talk about tension forces. So let's look at the free body diagram of the movable pulley. We have the weight of the mass, and then we also have the weight of the pulley. It's important to keep in mind that that's what they're showing right here. This plus W of pulley is the weight of the pulley, so the total weight coming through this is the weight of both items. And we here have our tension forces. The tension forces are going to be the same throughout a system. So if I have a tension force on cables or a tension force on wires or string or rope, it's going to be the same throughout an entire pulley system, as that states. Some different types of support reactions that we're going to be talking about: cables, ropes, and chains, pins, rollers, and a built-in end, or a cantilever is what it's also called. So we'll use different letters as we go through. So let's look at a cable support. Here I have a weight hanging from a ceiling. We have the tension force in the cable, which is what I told you before, always a tension force in the cable, and I have the weight of the object. This is just that I'm drawing a free body diagram. Let's look at a cable support in a different way. Here we have a sign being held up from an angle cable and from this cable that's going off horizontally. This keeps the sign from moving around a lot. You do see these quite often. Right off the bat, let's also remember I have two cables. The sign is hanging from both. The tension, the force of tension in both cables is exactly the same. So looking here, tension force in cable A, tension force in cable B, that is theta degrees from the horizon, and then I have the weight of the object that's pushing down. Here we have a pin. This we will actually be using quite a bit. And it's what they call a pin support. It has the triangle. All pin supports are going to have two reaction forces. One's going to be vertical on the y-axis, and then one's going to be horizontal on the x-axis. And they're labeled a little bit differently when we're looking at reaction forces. When I'm talking about the reaction force here, it's a joint at pin A. That's the placement of it, and it's in the x direction, which means it goes left or right. For this lower one, I have R sub AY. It's a reaction force at point A in the y direction. A roller support, you see it's a roller support because it has the ball. What's important to remember about roller supports is that the roller support allows this top piece, that if I push from this direction, the piece moves. If I push from this direction, the piece will move in the other direction. So we only have one reaction force, and it's going to be perpendicular to the surface. So in this case, we have RAY, which is reaction force A, or at joint A, in the y direction. Common support reactions is one that's going to have, and you see these in a lot of beams, a lot of truss bridges. It allows them to stretch and expand and contract so that a bridge doesn't just snap all of its bolts and fall into the ocean. But this is called a simply supported object because I have both a pin and a roller. But like I said, it allows for the expansion and compression of the bridge. So if we look at the free body diagram for a simply supported object, since I have a pin, it must have two reaction forces, one on the X direction, one on the Y direction. For the pin, or the roller, the roller, it has to have one, and it's going to be perpendicular to the surface. So it's going to be moving in the Y direction. Let's look at a built-in end, or a cantilever. So this is a picture that this is a shelf set into a wall. Here I have weight at the end of it. I need to create a free body diagram. Something to keep in mind is that I have two forces. One's going to be horizontal and one's going to be vertical, very similar to our pin support. And then I'm going to have one moment. Remember, a moment is a twisting force. So if I look at this specific item, if I have a weight coming down here at the end, the shelf, or whatever it is that we're talking about, is going to want to move in this direction. Well, I have to have a twisting force at the other end moving in the opposite direction, which we will have. First of all, at the end, it's end A, I have one of the two forces is my reaction force, point A in the X direction, reaction force, point A in the Y direction, and then here's my moment at A in the counterclockwise direction. So with all of our supports, I'll throw them all up here at once. So our support reactions, if something's is in contact with something else, it's sitting on top of it, you have a normal force. If it's attached by a cable, rope, or a chain, you replace it with a tension force in the free body diagram. If it's attached with a pin, you replace it with two reaction forces, one that is vertical, and then you have one that is horizontal. For a roller, you replace it with one reaction force perpendicular to the surface. The other one moves back and forth, so it doesn't have any force that acts on it is going to cause it to move. And then we have a built-in end, or a cantilever. You replace it with one horizontal, one vertical, just like our pin, and then you put in one moment. Here we have an example of a truss bridge. We have a pin support, a roller support. I have a weight coming down. They want a free body diagram, and this is what it looks like. On the pin side, I have my reaction force at pin A. On the Y direction, my reaction force, pin A in the Y direction, my 500 pounds of force, my weight. And then on the roller side, which is point C, I have my reaction force at point C in the Y direction, going perpendicular to my surface.